When we look in a mirror or we see a reflection of ourselves, what we see is a flipped image. And we can actually start to recognize what these flipped images are when we start to discuss chirality. From the Pearson textbook for organic chemistry written by Wade, we find that the definition of chirality is any image that is non-superimposable or non-identical to its mirror image. So to kind of break that down further, what we can kind of look at is an example here of chirality. There we go. So what we're going to do here is examine what happens with our hands when we put them in a mirror plane. So for example, if I were to put my left hand here on the left side of this line of symmetry of this plane or mirror as we call it, and we were to flip it like that, what we actually end up with is something that looks pretty similar to our right hand. So we compare our left and right hand, we can see that they're not identical to each other or non-superimposable when we line them up. Therefore, because my hands, when lined up and flipped over this mirror image, are non-superimposable, they are said to be chiral. Also, we can look at a different image, like a triangle here, and see what happens when we flip that across the mirror here. What we end up with is an identical image. So when we put these on top of each other, what we end up with is another triangle. Therefore, in our definition from Pearson textbook in Organic Chemistry by Wade, we find that something that is non-chiral or achiral is any image that is identical or superimposable to its mirror image. So why is this important? Well, chirality comes up quite a bit when we start to talk about organic chemistry. They're frequent in many molecules and in isomers or in enantiomers, which we will talk about later. But when we typically see chiral molecules, they contain something called a chiral carbon. And a chiral carbon is any carbon that is surrounded by 4 different substituents. So it's important then that we're able to recognize these chiral molecules and recognize these chiral carbons to see how they affect things. So looking at a few different examples here, we can start to talk about how to recognize them. And way one is to kind of draw a molecule, flip it over this line of symmetry of this mirror, and see what happens when we reorganize it or reorient it. So our first molecule here is an amine group and an alcohol coming off it. So first off, we need to recognize the chiral carbons within this molecule. And when we look here, we have a chiral carbon right here on this atom here and one right here. And the reason these carbons are chiral, like I said, is because they have 4 different substituents coming off of it. If we look over here, we have an amine group coming off on top. We have a long chain coming off over here attached to an alcohol. We have a CH group coming off the left side. And we have a hydrogen coming off through the back. So, assuming that's the same, when we look here, we can see that we have a CH3 group here, a hydrogen here, and a carbon chain attached to this amine later on. We can see that this carbon also has 4 different substituents, making it chiral as well. So looking at chirality, when we were to take this molecule and flip it on the other side of this mirror, we end up with a molecule that looks like this. And it's hard kind of right now to see what has happened to this image, so we can reorient it so that it's lined up with the chiral carbons back in their original orientation. So we can flip this to get the resulting image to look like this. And as you can see, if we were to put this molecule on top of the original image, we can tell that the mirror images have switched the stereochemistry of these substituents. So if we were to line them up on top of each other, we'd find that they don't line up perfectly. And from what we found before from our definition from Wade's textbook, any image that is non-superimposable or non-identical to its mirror image is said to be chiral. Therefore, this molecule here is chiral. Looking at a different scenario here, we can look at a cyclic molecule. Here we go. We'll use the same substituents here. And we can see that we have our 2 chiral carbons here following the same process that we used above. Now if we were to take this image and just like above, flip it to the other side, what we find is that we get the same exact image. So when we examine the substituents coming off of our two chiral carbons, we see that nothing has changed. And because the resulting reflected image across the mirror is the same as the original, and they line up perfectly, it is said to be achiral. So maybe this thought, you don't like reorienting the molecule. There's a different way you can start to examine these molecules to see if they are chiral or not. And that is through looking for a plane of symmetry within the molecule itself. What we find is that within chiral molecules, there is no symmetry within it. So if we were to examine this first molecule here and look for some sort of symmetry within this molecule, cutting it in half, we find that both sides of this molecule are different, so it does not contain any symmetry. But if we were to look at the second molecule and draw a line of symmetry down here and split these bonds, both sides are the same. So if we use this idea of line of symmetry to kind of justify what we found before, when there is no line of symmetry within the molecule, we end up with a chiral resulting image. But if there is a plane of symmetry, as in this cyclic molecule, we find that there is similarity and we have the same image resulting in an achiral image. So now that we're able to kind of recognize these chiral molecules in organic chemistry, we need to recognize how important they are out in nature. Oftentimes, these chiral molecules show up in pharmaceutical companies' drugs that they manufacture. One of the most famous of these was in Europe and when it was produced, and it was a medication called thalidomide. It was considered the wonder drug for its ability to treat morning sickness in pregnant women. But what they found was that this medication also caused birth defects within limbs of children when they were born. And the reason behind this actually comes down to the same concept of chirality. And what they found was one of the images of thalidomide was safe and very effective in helping pregnant women with morning sickness, whereas the other actually caused these birth defects. So if we look at the image of thalidomide, it's a long one here. Here's the original image we get, and this was the R image, and that comes from the naming process of how this stereo center lines up, because we're examining this chiral molecule right here. But if we were to flip this across the plane as we've done before, you get another resulting image. As you can see, this is the S arrangement from this chiral center. So as we examine the difference here, we can see that one of these has this bond coming out towards us, and this one has it pointing away from us. So if we were to line these on top of each other, we'd find that they are chiral because they are not lining up perfectly. And the importance of that is how these interact with our body. And what scientists found was that this chiral molecule right here, the S alignment, was the one that was responsible for birth defects in these children. So although these different molecules that are switched and reflected over this mirror and have different arrangements may seem pointless when we look at our hands or triangles, they make a huge impact in our life when we're discussing pharmaceuticals and how these interact with medications in our body. Thank you.